processes that lift air. If you want to make it rain, you need to lift air up. And the reason for that is if you want to make it rain, you need to have condensation. In order to get condensation, you need to cool air to dew point temperature. And if you want to cool air, the only way to do it pretty much is lift it up. So if you want to make it rain, you need to lift air up. Processes that cause air to cool to dew point. Yeah, there's 4 lifting mechanisms: convergent, convectional, orographic, and frontal. So those are words. Words are great. Let's look at some pictures. So convergent is when the air comes together, converges, coming together, and rises. This would be, for example, along the intertropical convergence zone. So you can imagine this is like, these could be the southeast trades, these could be the northeast trades, and then the air is rising in the ITCZ. Or it's just any area of low pressure. With low pressure, the air converges and rises. So number 1, convergent. For example, right here with the ITCZ, air is rising, it's converging, and it's rising. Convectional. So convection, you remember, as a mechanism of heat transfer. Convection, the air gets warm and it rises. That's pretty much it. Local heating, it could be a small scale effect like just on this field because it's darker and because it's plowed and it's all churned up, there's more moisture. That's going to evaporate and then condense and release heat, causing the release of latent heat, which is going to warm the air, so it's going to rise more. Or it could be land-water heating differences. I was going to say, I really hope the next picture is convection over Florida. So you can see over the ocean, not a lot of clouds, not a lot of little cumulus clouds. These are cumulonimbus, the larger ones, and these are smaller, just cumulus clouds. So these are all cumulus, and some sort of tropical storm spinning off of the Florida coast. But it's the difference in the number of clouds over the ocean, which is hard to heat up, versus over the land, where it's easier to heat up the land. So because you've got this long peninsula that's heating up because of the sun, you've got hot land, cooler water. So as the air rises, it pulls in this warm, moist air off the ocean that then rises, which pulls in more, which rises. So Florida, if you like thunderstorms, Florida is a great place to go. Another view, another day. This is also taken from space, showing the difference. In fact, you can see Lake Okeechobee, massive lake in the middle of southern Florida, that's not heating up. So there's no convectional activity over the lake. There isn't over the ocean, but there is over the land. That's just a great picture. Okay, orographic lifting. Orographic means it's getting lifted by a mountain. This is the most consistent. If you want to make it rain regularly, the best thing to do is to put a mountain someplace where it's going to get wind on a daily basis. The air runs into the mountain, it gets lifted up, it cools. Doesn't matter if it's stable, unstable, the mountain doesn't care. It's just sitting there and the air is blowing up over it. So as long as the air is being lifted by a physical barrier, it keeps cooling, you keep getting rain, it keeps cooling, you keep getting rain. As soon as you run out of lifting, you run out of rain. And even worse, or better, I guess, I don't know, is as the air rises, it cools, but then as it sinks, it heats up. So as it heats up, the relative humidity goes down, the clouds evaporate, the rain stops, and you get clear skies. On the rain shadow, this is the rain shadow side of an orographic barrier. So this would be Nevada, this would be eastern Washington, this would be eastern Oregon, this would be coastal Washington. The dry side is the rain shadow side, and these downslope winds, Chinook winds, they're called in the Pacific Northwest. In Europe, they're called Föhn, F-O-E-H-N, Föhn. And these are those downslope winds. We get them as Diablo winds, although they should be going the other way, down into the Central Valley. So when the winds come out of Oregon and then spill over the Sierras and drop into the Central Valley, they get compressed and they heat up. This is also what kicked off the fires in Oregon in August and September of 2020. These downslope Chinook winds, as they drop, they're going to heat up 10 degrees every kilometer. So if they drop 3 kilometers, they're going to heat up by 30 Celsius degrees, which is like, what, 58 or so? So enormous amounts of heating as the air sinks. In fact, the most rapid temperature rise ever recorded was 49 Fahrenheit degrees in two minutes. 49-degree increase in 2 minutes recorded at Spearfish, South Dakota by one of these downslope winds coming off the Rockies. So as the air came off the Rockies, it sank, heated up, sank, heated up, sank, and heated up, and increased the temperature 49 degrees in 2 minutes, 49 Fahrenheit. Orographic lifting, as the air goes up, it expands and cools. If it sinks, it's going to get compressed and dry out. And those downslope winds, Chinook winds. So an example, here we've got a Google Earth shot showing the ocean, the windward side of the Cascades, and then the leeward rain shadow side, like Yakima. They get 8 inches of rain. Over here, Mount Rainier, they get 126 inches of rain. So literally, a temperate rainforest as opposed to steppe and kind of semi-desert scrub. Oh, one of the rainiest places in the world. This is Mount Waialeale on the island of Kauai. They get 486 inches of rain because every day the trade winds come and get lifted up by this, and they get 486 inches of rain. The rain shadow side of Kauai gets about 20 inches a year. 486 inches a year, 20 inches a year. So this is right in here, the actual weather station on the top of Mount Waialeale. The helicopter pilot said, oh yeah, you can see the sun's been out for a couple minutes because the vegetation's turning brown. We were hovering and the winds were blowing sideways at 50 knots. And the helicopter pilot said, yeah, there's only a couple days, only a couple flights every year where you can see the summit when it isn't socked in with clouds. This is what 486 inches of rain a year looks like. I was guessing jungle, huge trees and vines, but no, it's like moss. It's just way too much. The wet side of Mount Waialeale, if you like ferns, it's a great place to go. And then the dry side, the rain shadow. This is the native vegetation. In California, very similar. The two patterns in California are latitude, under the polar front, latitude, under the subtropical high, and then elevation. So you can see like the transverse range with more rain. Down in Los Angeles, the transverse range. We've got the coast range. You can see the coast range with more rain. You can see the Sierras very clearly. And then you can see the Trinities and the Klamath Alps, and then going up into the Cascades. So Nevada, here's something fun to think about. 30 million years ago, the Sierras were not the mountain range that they are now. It would have been flatter, like much, much flatter. So that rain wouldn't have gotten stopped by the Sierras, and so Nevada would have been way wetter. Like, where'd it go? There's Death Valley. So here's, you can't really see Death Valley from the precip, but it's on the dry side. Like to get to Death Valley, you have to go up and over the Coast Range, which filters out a lot of the rain, and then up and over the Sierras, including the highest point in California, Mount Whitney, the highest point in the lower 48 states, just over 14,000 feet. And remember, once you go over a mountain, in order to get more rain out of that air, you have to cool it more, and the way to cool it more is to lift it higher. So once you're over the tallest mountain in the lower 48 states, you're not getting any more rain out of that by lifting it by a mountain. So the rain shadow, the Central Valley, the rain shadow, Nevada, the rain shadow, Eastern Oregon, Eastern Washington, Northeast California. Frontal lifting. It's when two air masses collide, they make a front. You've got warm fronts, and fronts are named for the more active blob of air. So the blob of air that's moving along, that's what the front is named for. So if you have a warm blob of air moving along and colliding with a colder blob of air, it's a warm front. If you have a cold blob of air moving along that collides with a warm blob of air, that's a cold front. So we got warm fronts, where a warm air mass moves into a cold air mass. The warm air moves up and over the cold air. Warm fronts are about 1,000 kilometers wide. They move about 25 kilometers an hour. Here is the diagram out of the book of a warm front. They move along at 25 kilometers an hour. Here is the warm air that is slowly trying to push this cold, dense air out the way. And there is this distinctive set of clouds. First, there are cirrus clouds. So you have to imagine this entire system is moving from left to right across the screen. The cold air is going to get gradually pushed out of the way. So if you were standing here at the right edge of the screen, you'd see cirrus clouds, and then as the storm goes by, you'd see cirrostratus, altostratus. As they get lower and lower and lower, finally stratus, and then rain. And if you think about the way our storms come, usually 24 hours out, you see cirrus clouds with those wispy effect. Halo or a ring around the sun or the moon tells you 24 hours later you're going to get a storm. That's because cirrus clouds are at the leading edge of a warm front. So you have cirrus clouds, and then as it moves along, you can see that the altitude of the clouds just gets lower and lower and lower, and then you have gradual gentle rain. So from the actual boundary layer on the ground to the cirrus clouds, about 1,000 kilometers. With a cold front, the cold air mass moves under the warm air mass. The cold air lifts up the warm air. In fact, the cold air is always lifting up the warm air. Warm air is less dense, so whenever warm air and cold air collide, the warm air is going to get lifted up. Cold fronts are about 400 kilometers wide. They're more narrow. They move faster. They travel about 40 kilometers an hour. So here we've got a cold blob of air moving along and lifting up this warm air. So it moves faster. The air gets lifted faster. So you get heavy rain for a little bit, and then you have clear, cold air behind. And if you think about the way our storms end in California, typically it like pours for a while, and then you wake up the next morning and it's clear blue skies and it's cold. And it's cold because it's this cold polar air mass. From the cold front, they're about 400 miles wide if you look at it on a weather map. And here's the symbol for a cold front, those blue triangles. Probably should have said. Symbol for a warm front, you can't see it. We'll have to look for the video. So I'm going to start with this warm front. So if you were standing here, the warm air is going to push the cold air out of the way. And so if you notice, the altitude of the clouds is just going to get lower and lower and lower and lower until you end up with the nimbostratus rain clouds. If I back it up for the cold front, it's moving faster. The warm air gets lifted much more rapidly. So you get intense rain, often thunder, lightning. I don't think we get that too much in Sacramento, but that would be associated with a cold front. And then it's just cold, dry air behind it. I've put the animation in the lecture slides. So when you watch the lecture slides, I would watch the animation and it's got narration. I would turn it on and listen to what Pearson has to say about cold fronts and warm fronts. So here's a cold front moving along. That's a cumulonimbus cloud. There's another one. Looks like they've got a bunch of cumulonimbus clouds embedded in the front end. It would be moving from the top down. So there'd be warm air in here that's getting lifted up as this cold air is moving towards the bottom of the page. More lifting of air. This really impressive Midwestern supercell. Probably tornadoes are going to be spawned from that. Big hail. So if you put a cold front and a warm front together, you get a mid-latitude cyclone. Mid-latitude tells you what latitudinal zone it's in, the mid-latitudes. And cyclone tells you it's air flowing into an area of low pressure. So it's a warm front and a cold front spinning around a center of low pressure. And they're caused by the conflict between the warm maritime tropical air mass and the cold continental polar air mass. So it's the conflict between the natures of these two different air masses. And once that conflict is resolved, the whole storm goes away. So here we've got a warm front. So you've got warm, moist air coming up. You've got cold, dry air coming down. There's a center of low pressure here. This is the symbol for a warm front. This is the symbol for a cold front. And this is the symbol for an occluded front that I haven't talked about yet. So we've got warm air getting lifted up over the cold air. And then over here, there's cold air pushing along, moving along the ground. That cold air is running into this warm air and lifting up the warm air. This was a satellite picture from this year with a cold front and a warm front and an occluded front over in here someplace. So the whole system would be rotating counterclockwise. And this warm air is coming up. And here's the boundary layer between the warm air down here and the cold air up here. So the warm air is running into the cold air and getting lifted up, making a warm front. So you've got all this warm air down here. Over here, you've got cold air coming out of the poles, and that cold air is moving along. And as it moves along, it's going to run into the warm air and lift up the warm air, making a cold front. You can see behind the cold front, it's clear. So this would be the day after the storm, when it's all clear and you've got blue skies and cold air, because that cold air is coming out of the poles. I have put a whole bunch of examples for you to take a look at. If you click on it, it'll open up earth.nullschool.net. And it'll take you to an example of exactly what we're talking about. So I'll click through a couple. So right here, you've got warm air coming up, colliding with cold air. And then over here, you've got cold air coming along, colliding with this warm air. And if we turn on temperatures, 16 degrees, 11 degrees, not a huge difference in temperature differences. If we turn on the total precipitable water, you can see that there's pulling, the warm air is bringing moisture up and the cold air is not. The cold air is very dry and the warm air, 33 kilograms of water, 10 kilograms of water. Let's look at another one and see what happens. Oh, there's two. Oh, yeah. So fronts are pretty easy to find on weather maps, especially the animated ones, because the wind direction changes 90 degrees. So here's this warm air coming up, warm air coming up. There's the center of low pressure. And then this is that cold air coming down that's running into the warm air. So there should be a line of clouds here and a bunch of clouds over there. Same deal here. Got cold air coming down, warm air coming up, an area of high pressure, rotating clockwise, low pressure, rotating counterclockwise, high pressure, rotating clockwise, low pressure, rotating counterclockwise, high pressure, rotating clockwise. And then down here, this is actually the ITCZ. You can see the northeast trades moving down, and then these would be the southeast trades moving up. So if I turn on the total cloud water, aha, you've got a cold front, relatively narrow cold front, and a big old wide warm front. And then as I said, along the ITCZ, you've got all these convectional clouds. So I've put a bunch of examples. I hope you enjoy that. I hope it makes sense. If not, show up to Zoom. Give me a call, whatever. Let's hang out. Let's look at wind and rain patterns. Here is another animation. I think this is so useful, because I can't draw this on the board, and even if I could, we're not in class together anymore, so we don't have a board. So, cold front, warm front. Here's the warm air coming up. Here's cold air, cold air, cold air, warm air, warm air, warm air. The whole system is going to rotate counterclockwise as it moves across the United States. So there's two patterns of motion with these storms. In fact, if I go back and we scroll forward, you'd see that the whole system is going to move from west to east. It's going to move across the country. This is over 2 days. So typically it will take a week to move across the whole U.S. The cold front, you can see, is moving faster than the warm front. So it actually catches up to it, and then all the warm air is going to get lifted up, and you have an occluded front behind it. When the cold front passes the warm front, because the cold front, remember, can move at 40 kilometers an hour. Warm front's moving 25 kilometers an hour. And in just a second, they're going to turn on the side view that I think makes this entire video worthwhile. Yeah, let's get going. There it is. Okay, so as it moves across, as it moves along. So here we've got cold air. That's this cold air. That cold front is this cold front. This warm air is up here. This cold air is the cold air along the ground. So the warm air is moving up over the cold air. The warm air is moving up over the cold air. And then over here, you've got the cold air lifting up the warm air. So So the storm begins because this blob of warm air is colliding with this cold air, and then this cold air is colliding with that blob of warm air. So this is warm and moist, cold and dry, cold and dry. So there's conflict because they're totally different in terms of temperature and humidity. So as they move along, and now we've got occlusion starting because the cold air mass, in fact, I'll just let it continue for a little bit. So after occlusion, the cold air is on the ground, the warm air has been lifted up. So in the troposphere, the surface is heated by the sun. The air next to the ground is heated by the ground. So the temperature profile of the troposphere should be the warmest air at the surface, and then as you go up, the air gets colder and colder and colder. Okay, but now everything's backwards. You've got cold air on the ground, you've got warm air lifted up. The cold, dry air was bouncing off of the warm, moist air because they had different temperature and humidity characteristics. Well, now the cold air along the ground is going to warm up. All the rain produced a lot of moisture and precip that's going to evaporate and humidify the cold, dry. So the cold, dry air is going to get humidified and warmed and become warm and moist. The warm, moist air got lifted up where it got cold, and as it got cold, you get condensation, so the warm, moist air is now cold and dry, and at some point there's no difference. The reason the cold air can lift the warm air is because of the difference in temperature. But once the warm air is lifted up, it gets cold. Once the cold air is on the ground now, it gets warm. So everything just kind of blobs together, and the storm just fizzles out because there's no more energy for conflict. So one more time, we've got the cold air catching up to the warm air. All that warm air is going to get lifted up. You're going to get more rain. But then the same process that started the storm is the same process that's going to end the storm, because there's no more moisture, there's no more energy. Mid-Latitude cyclones. Typically they take a couple days. The process of starting one is called cyclogenesis. Cyclo referring to cyclone with air flowing into an area of low pressure, and genesis means the birth or the start of. So it's how these storms start, usually along the polar front. With the open stage, the air starts to move around. The warm air is moving northwards, the cold air is moving southwards. The warm air is moving northwards with the westerlies, and the cold air is moving southward with the polar easterlies. After the open stage, you get rotation, you get a center of low pressure developing, and then both air masses start to rotate counterclockwise. You can then get occlusion when the cold air catches up with the warm air and actually passes the warm front because it's going faster. And then all the warm air gets lifted up and gets cold. All the cold air is on the ground, it gets warm, and then it just dissolves and goes away because there's nothing left to create conflict. The diagram out of the book is showing the same storm. Here it is in the open stage with rotation, and then over here occlusion has already started, and the next thing that's going to happen, once you're in occlusion, here's the side view with the cold air and the warm air lifted up. Everything is going to mix together, and the storm is just going to dissolve. We don't really get summer storms in California. We get winter storms when the Hawaiian high shifts south. Different diagrams showing the direction of wind, because one of the things that you'll notice is, and you should be able to read wind barbs, so we've got wind coming out of the southwest, wind coming out of the northwest. You can see the green arrows are indicating the direction of wind. So if you were right here in Wichita, in fact, even better, if you were right here, you'd be experiencing cold, clear 40 degrees, dew point temperature of 28. And then after the warm front goes through, the wind is going to shift, and now the wind is coming out of the southwest, and it's warm and it's moist. And then after the cold front comes through, it's going to get really cold and really dry. Like the dew point's going from 69 down to 46. The temperature's going from 78 down to 47. The wind is coming out of the southwest, coming from the southwest, and now the wind is coming out of the northwest. So the wind direction is going to shift 90 degrees. Instead of being warm and moist and rainy, now it's going to be cold and dry and clear. Typically, that's what happens as a mid-latitude storm works its way through. So you have the same storm over 3 days. with rotation, occlusion beginning, and then occlusion with the storm on its way to dissolving. Another diagram showing how a storm is going to work its way across the United States over the period of a couple days. You've got the warm air and the cold air, and then with the occlusion, everything gets backwards and it dissolves. Here we've got one storm over 3 days, or you've got multiple cyclones. Yeah, usually there's 3 to 7 storms in the polar front on any given day. Here's the open stage. Here the wind is out of the southeast and it's cloudy. Wind is out of the southwest. Remember, the wind comes from the end blowing towards the circle, and then here the wind is coming out of the northwest. So you can see here 66 degrees with a dew point of 63. Dew point temperature is the temperature. If you cool the air, it's going to get to 100% relative humidity at 63 degrees. Over here, 27 degrees. Over here, 18 degrees. So those dew point temperatures are very low. The bottom temperature is the dew point. The top temperature is the air temperature. So here the wind is coming out of the south. It's 66 degrees. Here the wind is coming out of the west, and it's 37 degrees with a dew point of 21. And I was going to say, this is already an occlusion, so the next thing it's going to dissolve, and it's toast. Let's back that up. So there's day 1, day 2. Once it's once you have occlusion, once it's in the occluded stage, it's on its way to dissolving because the warm air has been lifted up where it's cold. The cold air is on the ground where it's warm. Mid-latitude storms.